Good afternoon, everyone, and welcome to today's webinar, Electrical Safety in 2012, hosted by EC&M Magazine and sponsored by I-Gard. My name is Mike Eby, Editor-in-Chief of EC&M. I will be your host for today's event. In a few moments, I will introduce our speaker, but before I do so, I have a few housekeeping items to run through. Throughout today's event, we encourage you to submit questions you might have on the topic. To submit your question to today's speaker, simply type it in the question window on the right-hand side of your screen, then hit the Submit button. Please note that you can submit a question at any time. In fact, we prefer you submit them as they occur to you so we can prioritize them and get them ready for the Q&A session. If at any time you have issues with your audio stream or advancing of the slides, simply hit your F5 key to refresh your webinar console. In addition, the EC&M and I-Gard logos are hot linked. So if you want to visit either website during the webinar, you can click on either logo and a new window will open on your screen that will allow you to go directly to those websites, but it will not take you out of the event. Today's sessions are being recorded and will be available on the EC&M website within the next week for you to review. You'll be notified by email when the archive is available. And if for any reason you still need help during the live event, please press the Help button on your player console and someone will assist you. Now that I've run through those housekeeping items, it's time for me to introduce today's speaker. Dilip Molla received his BSEE degree from West Virginia Institute of Technology. He's a longtime member of NEC Panel 5 and is a key member of the NFPA 70E Technical Committee. During the 2012 Electrical Safety Workshop, he received the IEEE Charles Proteus Steinmetz Award for his dedication and work over the last 25 years to develop safer equipment and promote safety standards to reduce the number of electrical-related accidents in the workplace. With experience designing and constructing the electrical infrastructure of petrochemical facilities while with Union Carbide from 1976 to 2001, Dilip employed his safety by design concepts, examining each infrastructure design aspect to maximize safety, resulting in many innovations. In 2007, for his extraordinary contributions to the petrochemical industry, he received the coveted David Asbill Award. And back in the 90s, he served as chair of the electrical functional team of the Process Industry Practices Group, convincing industrial industries to share electrical safety designs. Today, he serves multiple IEEE Standards Association working groups related to the petrochemical industry, safety and arc flash hazard analysis, and recommended practices to improve electrical safety. So it's my pleasure to turn this session over to Dilip, and let's get started right now. You ready, Dilip?
Yes, sir.
Okay.
Thank you very much for attending this session. My name is Dilip Molla, and I'll try to introduce you some of the concepts. I'll reinforce some you already know. Okay. Our main focus in industry, doesn't matter whether it's a petrochem industry or any industry, is few things we want and few things we do not want. We all want process reliability, electrical equipment not to be damaged, and don't want anybody to get hurt. What we do not want is unscheduled process interruptions, which can create environmental concerns or safety concerns, or electrical equipment getting damaged due to arc flash or short circuit, or in the process, we don't want anybody to get hurt either. Safety is probably number one in every industry right now. What does ground fault and arc flash do? Essentially, they damage the equipment. They hurt people. And they cause power to be interrupted when we do not want to. That means there's a lot of business losses after the fault. Now, how do we do that safety? There are two definitions. Hazard is one, and risk is other. Hazard is something we have potential to cause harm and damage. Risk is what is the likelihood that event will occur and result in damage. To be truly safe, we have to reduce both. Obviously, more hazard we reduce, better we are. If we cannot do that, then we reduce the frequency the best we can. This is an excerpt from Occupational Safety and Health Management System, recognizing electrical safety is not an island. It belongs as part of the total safety management system. This is an excellent document referenced in NFPA 70 also. And look at 1.3. This standard is applicable to organization of all size and types. Primary purpose is to provide a management tool to reduce the risk of occupational injuries. And all of you probably know electricity is a little toxic substance. You touch it, when you're not ready to, you'll get hurt. This is also a hierarchy of method has been suggested in ANSI Z10. And you can see that first is select a manageable task. Identify what the hazards are. Define possible failure modes. And can somebody get hurt? Estimate the frequency and duration. Anything you can do that. Assess the severity of that injury. Once you go through this process, you know how to manage the risk. Just for your understanding, you cannot manage the hazard. Hazard is there all the time. You just manage the risk so somebody doesn't get hurt. This is some of the example of risk assessment that you can see. If somebody can get hurt severely or get killed, that is a very high risk or serious risk. Normally, electrical people should not proceed when a risk is identified as higher. If it's a serious risk, high priority, then you have to take some remedial action, either at that time or before you do the work. Then you go to medium to low risk. The low risk level is when you consider there's going to be inconvenience, but the risk is acceptable. Now, in industry, you have to be very careful. Every risk is not acceptable. These are some statistics, and you can see from U.S. Department of Labor, in 7-year period 1992 to 1998, over 2,200 workers died, and over 32,000 were injured away from work due to electrical shock or electrical burn injuries. So you can see that a lot of people are getting hurt. Now, one thing you also know, people depend on OSHA. OSHA requirement is only if there is a one fatality or 2 injuries that have to be reported. So OSHA is normally on the lower side of the injury base. This is some of the loss potential. What you see in yellow is industrial, and what you see in blue is commercial. And you can see as the losses get higher, how much industrial losses mount up. And all of us in the business to make money, and to make money we have to keep the process running safely. A lot of costs are indirect costs, legal costs, possible fine, investigations. This was collected by Capshell Incorporated, which is owned by Dr. Mary Capelli Shellpfeffer. And you can see that preventing worker injuries. There are 5 to 10 arc flash explosions that occur in electrical equipment every day. And our experience is not everybody is reporting it. If you ask yourself how many times you get a shock or flash and you report it. On the bottom paragraph you see some statistic from NFPA that how many fires were caused. These were tabulated as caused by electrical incidents. Again, looking at the risk assessment matrix, if this is catastrophic or critical, you see some red blocks. Red blocks mean nobody should be working on it. If it's a orange or yellow, then you can take some precaution because the goal is that you can do work very safely. If you cannot do work safely, you do not want to do that work. It's the same matrix you see for the serious injury. It's a high priority. Remedial action must be taken at the earliest opportunity, that sometime you notice some hazards while you were doing the work. This came from NCZ 10, Hierarchy of Hazard Control Measures. The best method is eliminate. You see on the left-hand side, what is the control effectiveness, and the right-hand side, the life cycle value. Unfortunately, when you look at the short term, maybe you don't see the total picture. Elimination. Eliminate the hazard during design. Substitute with the less hazardous equipment. Have engineering controls, something that automatically stop people from doing something. And you see the lower end of the spectrums are warning, administrative control, and personal protective equipment, because they all require some kind of action from workers. Industry statistics include that workers will make an error 1 in 10 times. So you can see that why they're not very effective. You have to monitor them. Elimination is the best method. You remove that hazard by design. OSHA believes in elimination also. This is an excerpt from OSHA requirement. Live part to which an employee may be exposed shall be de-energized before the employee works on or near them, unless the employer can demonstrate that de-energizing introducing additional increased hazard. Keep that in mind, the key word, unless the employer can demonstrate. It's not employee to demonstrate, it's employer's responsibility. That de-energizing will introduce additional increased hazard. OSHA in one case did issue an interpretation that loss of revenue may not be considered all the time as infeasible. What is inconvenient, I don't want to, doesn't fit in OSHA definition. So any time you can take the power off, de-energizing before working is always the best option. But all of you know that sometimes just the process of de-energizing can expose somebody to a hazard. Now let's shift to system grounding. That's the focus going to be. There are 3 grounding methods for system. This is different than equipment grounding. You can have an ungrounded system that was pretty normal in process industry till 60s. You can have a solid grounded system, which is still very widely practiced for the low-cost option. Or you can have resistance grounded system. We'll try to go one by one, just the highlights of each system. Ungrounded system, normally, you don't have to do anything. This was a recent electrical fire that was solid grounded system. And you can see the losses were 400,000. And the question was asked during investigation and legal cases, was the grounding method chosen by consulting engineer facility owner a contributing factor? Answer was yes. If you have solid grounded system, it's a cost saving. They're simple, but they create more flash hazard. Anytime you see in this equipment, if you can see on your screen, that black deposits, that means it was an arcing fault. Arcing faults are preventable. If it's a solid bolted fault, you would not see any deposits on the equipment. So anytime you go for investigation, keep that in mind. Resistance grounded system prevents your equipment to have damage from arcing faults. Some other reference from IEEE standard. This is for delta grounded system. If the ground fault is intermittent because it's spark and allowed to continue, system could be subjected to severe voltage, which can be 6 to 8 times. Now, how did we come out 6 to 8 times? In theory, they can go forever. But at 6 to 8 times, other equipment will be damaged and the fault will clear. So you can see the ungrounded system have a lot of transient problems. Okay. This is you can see the sketch that arc will restrike on a ungrounded system and voltage will keep on building up till something else clears. That is the reason it's so damaging. Why would industry use it? Because the first fault would not cause an interruption in the process. That was industry's goal. Other problem in the ungrounded system is you cannot have a fault detection. So what is a high-resistance grounding system? If all of you know, basically, Ohm's law, current is equal to voltage divided by impedance or resistance in the circuit. So if we want to cut down the current fault level, all we have to do is insert some impedance in there. And that is what the basic for high-resistance grounding is. We will bring it down to 5 amps or less than 10 amps. So during first fault, you do not have any arcing flash. At 10 amps, arc cannot sustain itself and it will go away. There is a very well-known author, Duncan Jacobs. That's from his book, that 95% of all electrical faults are phase-to-ground faults. They start as phase-to-ground, and then they migrate sometime to phase-to-phase or bolted faults. But if you have less than 10 amps, there is no current left for it to restrike, and it self-extinguishes. That is the reason high-resistance grounding has been promoted in industry since 1960s. The industry I work with, we have been using this from 1960 on, high-resistance grounding system, because it allows us the benefit of ungrounded with not the disadvantage of ungrounded. This is a reference from IEEE Standard 141, commonly called Red Book. They tell you the same thing. High-resistance grounding has the same advantage as ungrounded system, in the sense the first ground fault would not interrupt you. That was the primary responsibility of Delta system, was ungrounded. But the advantage is that you don't have transient currents and overvoltage associated with ungrounded system. Others see the highlighted part under it. There is no arc flash hazard in a high-resistance grounding system as there was solid grounded system, since the fault current is limited to approximately 5 amps. Now keep that in mind. Later on we'll go. This is only true for the first ground fault. Since 95% of the faults originate as ground fault, if you can remove that before the second happens, you do not have an arc flash problem. Under it you see recommended practice for protection and coordination. Came from the Buff book. And look at very clearly what it says. Ungrounded system offered no advantage over high-resistance grounding system. Continuity of service, and they have disadvantage of transient overvoltage. Now you can see that 141 and 242 basically say the same thing. IEEE realized it too, and we are trying to incorporate everything in one standard. The Green Book, which was just revised last year, and I'm the vice chair for that book, it tells you the same thing. Okay? The reason for limiting the current by resistance to grounding may be one of the same. One is always continuity of power. Second is arc blast or flash hazard. If in your facility or somewhere you saw that motor terminal boxes or enclosure doors flew apart during fault, that is because of solid grounded system. It should not happen if the fault is cleared in high resistance grounding system. And 141, the Red Book, essentially says the same thing. Limitation of ground fault current to prevent damage to the equipment, prevent injury to people. So all the good qualities are available as opposed to solid grounded system. This is just to show you the path. If you look at the red path, red arrows, when you have a solid fault, and if you write down where you are attending, Ohm's law, current is equal to voltage divided by impedance or resistance. Since this path is so low, resistance so low, current will go to almost to infinity. If we can introduce a high resistance grounding system in there, current is limited. So that's the basic theory for that. which is very simple and credited to a lot of preventing of arcing faults. So first step is eliminate. Simple method to eliminate, don't have electrical system. But unfortunately, that's not practical. Next is substitute with less hazardous equipment, system, or energy. That's where higher grounding comes in. And at the end of the session, we'll go through complete and go see the pros and cons of each system. This is an equation that appears in IEEE 1584, which is considered the best available standard as of now for calculating incident energy. I would not go through all the equations, but you can see that it requires some calculation. And one thing is working distance. You need the working distance, what is going to be, where you're going to work. People say we do not have a problem because we work too far, but sooner or later you have to come close to the equipment. And the gap is distance between electrodes. This is some industry data. If the fault can be cleared, and this is based on 50,000 amp voltage fault current at solid grounded system at 18-inch working distance. If you can clear the fault in 35 milliseconds, which is about 2 cycles, you will have minimal damage and 2.9 calories, less than 3. Now compare that when you have 100 milliseconds, which is 6 cycles. And you can notice that as the time goes up, energy goes up. If you have 500 milliseconds, which is half a second, which is an eternity in an electrical system, you can see the energy, almost 42 calories per centimeter squared. Person cannot survive this on bare skin. Even if you have protective clothing, you're still liable to have blast pressure damage. This is showing you 2 curves. Anything you can interrupt before the green line, that means it will have minimal damage. Anything you go above the red line is going to be a tremendous damage. So you're trying to keep, and you can notice all of them are based on how fast you clear. The horizontal axis is time, vertical axis is current in 1,000 of amperes. So if you can clear the fault quickly, that is the one technology. If you cannot reduce the fault, you cut it down, reduce the time to clear it. So how you substitute a hazard with a lower level? We have all accepted electricity is a hazard. You can limit the time the fault persists before you clear it out. It could be done by a maintenance switch. Or you can use current limiting fuses or breakers. Now, you have to be careful. The current limiting fuses or breakers are only limiting in the current limiting range. Every fuse is not current limiting. Every breaker is not current limiting. So current limiting fuses or breaker will reduce the time. So will maintenance switch. And we go through, we'll explain to them. You can have zone selective interlocking relay, or the latest technology is optical arc detection, because when the flash happens, the first thing you see is light. Then you experience the sound and the pressure. So if you can take the first method that you can get, you're going to cut down the time that flash persists. Current limiting fuses. All of you are probably familiar with NEC, National Electrical Code. In 240.2, they will tell you that what is the metrics or what is required for current limiting fuse. You can use when there are high, very high fault current conditions. Okay? They protect the equipment from significant thermal damage. Now keep that in mind when you're using current limiting fuse. Any breaker downstreams may or may not be protected. That's a pretty common misconception that everything downstream is protected. For downstream device to be protected, you have to have a passive device, something that will allow current limiting fuse to blow. Otherwise, you'll have transferred the problem downstream equipment. This is an example with the current limiting fuses or some fuse installed. If you look at the top line, that shows you arc flash boundary. If you have a 640 amp current limiting fuse, and this is based on 22.6 Ka, three-phase voltage fault. Actual test results were done at Busman facility. That's where we noticed that. You can see that even with the 22 Ka, you have only 5.8 calorie. If you have a current limiting fuse, and if it's in a current limiting range, it is dropped down to 1.6. A rule of thumb, current limiting fuse will limit about 15 to 20 times on arcing current. Now, last column you see, you have a 30 amp fuse. On 26 Ka, it goes in current limiting very well. So you have a 6-inch arc flash boundary and only 0.25 calorie per centimeter hazard. What is the arc flash boundary? Where the incident energy is going to be 1.2 calorie per centimeter squared or higher. That is the energy medical field tells us can cause onset of a second-degree burn. This is the same what you see the test. The test 4, you can see the energy. It all started from here. It took it all the time 6 cycles to interrupt. And you can see as it keeps on going down as opposed to test 3. Energy has been substantially reduced. So if you can highlight the area between these curves, that will give you the energy. Now at 30 amp fuse, you can see how quickly it cleared. So wherever you can use smaller fuses, that's where you should use, as opposed to using the biggest fuse you can put. You should check your system and use current limiting fuses to lower level. Okay. Other technology, maintenance switches, zone selective interlocking, and optical arc detection. Okay. What is a maintenance switch? When you have two protected devices in series, normally you cannot use instantaneous. Two instantaneous cannot be coordinated. So you put the upstream device on what we call short time. Give it a little more time to clear the downstream fault. What convenience it gives us, a little more time for clearing the downstream fault, also causes us to have excessive arc flash. It takes a long time. So what maintenance switch does, that when somebody is working on it, you click the switch, upstream device is set at instantaneous. So it'll clear faster. Of course, it requires some human action, so it cannot be considered as an absolute that it'll work automatically. Now you have to also go back and reset them. This is one of the options allowed in National Electric Code 2011 under 240.87, 240.87. One of the options is allowed. Just to give you an example, how does it work? Person is going to work on a breaker, racking in and racking out. He or she is very close to the breaker, and just for discussion's sake, for this calculation, the voltage fault current was 30,000 amps. Arcing fault value is 12,000 amps. Now in industry, 30,000 amp is not considered very high current. Or some of our switchgear is rated for 85,000 or even 100,000 amps. It has a 2,000 amp main breaker. When this person is racking it in, if the fault happens on the line side stabs or even on the load side stabs, it'll try to migrate to the line side, so upstream breaker has to take it out. Now, in this slide, you can see how long it takes. Okay? 12,000 amp will trip the breaker. It takes about 0.5 seconds or something to that effect. If you calculate that arc flash, based on that time, you'll see about 25 calories. Even that person has a suit on. Arc flash suit is not an armor. He's still going to have blast pressure. It's very likely the person will be thrown back. Why it says equation for arc in a cubic box? Because that's what you have in an enclosure. You do not have an open air system. Okay. Now, if you convert the maintenance switch, which will trip a lot faster, and you can see the energy has gone down to 2.3. That is tolerable. That's a acceptable risk if you have protective clothing on, because the blast pressure may or may not be that high. So basically what maintenance switch does, reduces the time, clears the fault faster. Other technology, zone selective interlocking. Like I explained to you, when we have two devices in series, we cannot set both at instantaneous. So this one is normally set at, the upstream main breaker is set at short time, and feeder breaker is set at instantaneous. What does zone selective interlocking do? This is basically a smart system. If the fault happens downstream of this breaker, these are all interconnected. This device is telling to main breaker, I see the fault. I will clear it. So you hold on. Becomes a backup. In the meantime, if the fault happens on this side, since the fault can only be cleared by downstream device, this device senses that this is beyond the capability of feeder breakers. So zone selective interlocking will take the main breaker off. Now this is to prioritize safety over reliability. You can see that as soon as the main breaker trips, everything in the switchgear will trip. So that still protects the people at the cost of reliability. This is just some example. If you don't have zone selective interlocking, or you do, clearing time with non-selective zone interlocking, which is going to be short time, is about 0.4 seconds, and you can see you get about 33 calories instant energy. If you can have zone selective interlocking, you have cut down the time to 1/10 of a second. Now you have 8.31. People who are math experts, you can probably definitely see the relationship. When the time went down by 4, so did the energy went down by 4, because incident energy is proportional to I squared T, squared of the current times the time it takes to clear. And this is based on 50 kA voltage fault current, same thing what we had before. Third is optical arc detection. When an arc flash happens, since the speed of light is the fastest, that is the first thing you see. That is the reason you see anybody exposed to arc flash, whether they are wearing protective clothing or not, will be momentarily blinded. Vision will come back, hopefully. So we use that property to interrupt, cut down the clearing time. This is some of the sketches you can see when you have arc flash optical relay. Okay? Now, anytime an air brake breaker opens or closes, it will have an arc. You don't want it to trip every time it's doing its normal job. So to provide a backup, you have a current input through it. That means two conditions have to be satisfied before the breaker trips. Current has to go very high value, and flash has to be happen at the same time, which will allow the breaker to trip. You can set it up as multi-layer. You can have it that I'll only trip some of the feeder breakers, or you can trip the whole thing. That's up to you. But this is a very fast method. They'll cut down the incident energy. Now look at the comparison with optical. If you had typical 51 relay, which is called timed over current relay, clearing time is 3 seconds, your incident energy is 37 calories. If you have instantaneous, you have cut down the time to about 0.45 seconds, your incident energy dropped to 5.4. Now, if you have optical detection, you've cut down time to 0.05 seconds. Only thing is slowing it down, how fast the breaker can operate. If breaker could operate instantaneously, it'll approach zero. So optical arc detection, you can see that, you can have a coordination, and you have cut down your incident energy from 37 to 1.2. This is how optical arc detection works. You have arc sensors in every cubicle, and then have a current unit. It gives a signal to a main unit to trip. It's a very fast, where process continuity is not the main concern. This is a very fast method available. Of course, keep it in mind, this is only contingent upon the breakers have been maintained properly and they'll trip on command. All this is doing is giving, whether it's zone selective interlocking or optical detection, all they're doing giving a signal to the breaker to trip. Breaker has to be in a proper condition to trip. If it's a DC operated breaker, you need to have control power available. Look at the same comparison. You have a 480 volt system. Short circuit current is about 41 kA, working distance 18 inches. Now this working distance is not from the front of the cubicle. This is from where the arc source is. So arc source could be inside. Based on that, incident energy was calculated to more than 100 calories per centimeter squared. Is the clothing available for this? Yes, it is. But the blast pressure is going to be so high, the person, even with the flash suit, will be thrown away. If you put an optical detection, the same parameters of the short circuit and working distance, you can see you have reduced it to about 5.9 calories per centimeter squared. That risk, after you do analysis, may be tolerable. But keep that in mind. All these things you can only use after employer has demonstrated that it's infeasible or greater hazard to de-energize. They are not a substitute for not following OSHA requirements. Next method we'll discuss is engineering controls. What are the engineering controls? Something that takes effect automatic. No human intervention is required. One equipment for that is arc resistant switchgear. A standard switchgear, which nothing is standard of course, something that has been tested on bolted fault has not been tested on arcing fault at all. When you have a bolted fault, only thing you have is mechanical stresses, so door would not see anything. When you have an arcing fault, you will see a tremendous amount of blast pressure, and door will blow away. This is the reason you need arc-resistant switchgear, because door is reinforced to allow the arc to dissipate from the top of the cubicle to protect person. Of course, when the fault happens, inside the arc-resistant switchgear may or may not be in workable condition. It may have to be rebuilt or repaired or something to that effect. Now, also keep it in mind, arc resistant is only arc resistant when the doors are closed. When the doors are open, the property is not available. You can have remote racking of breakers. Since industry statistics prove most of the faults happen when breaker changes state or when they're racking in. So you can have a remote racking system so somebody is not there. It does not reduce the hazard, but it does reduce the risk. Equipment may be damaged, but person may or may not be there to get hurt. One technology people are not using is very excellent is infrared windows. Infrared tells you the temperature is rising and arcing is liable to happen, or arcing is already happening. You can open the door and check it, or put infrared windows during design stage, so you can check that hot spot or something from outside. If you're familiar with NFPA 70E 2012 under table 130.7 C15, it'll give you what protective clothing you need, when you are doing infrared thermography. Now, unfortunately, as of now, manufacturers don't give you any credit for extending the maintenance if you do infrared inspection. Industry is working on them to allow that as one method of preventive maintenance. In high voltage, first thing will happen is a breakdown of insulation, which results in partial discharge or corona. There are failure of the insulation, and this is infrared and partial discharge are both based on that if you can catch it before it goes to fault mode, you have minimized your interruption. So if partial discharge activity occurs, that means insulation failure is imminent. Now technology is available, they can almost predict how much time you have. This has been very extensively used for medium voltage switchgear and motors. Next method, let's look at the warning administrative controls. Okay. First always is eliminate the hazard during design. In your automobile, you have hazard eliminated by design. Between drive and reverse, you have a neutral gear. If you didn't have the neutral gear, a nameplate wouldn't do that hold for so long before you change the gear. Substitute risk for a lesser one. Redesign the process to put some more engineering controls. Engineering controls are very smart. They do not have any emotions like humans do, and if they're working correctly, they will repeat exactly what they were intended to do. Safe work practices and personal protective equipment. PPE, as commonly called, is the least desirable. That's part of administrative control. Again, coming back to wants and don't wants. Now let's see unsafe work condition and safe work condition. This is the hierarchy, and you look at that almost at the end, lower level is PPE and administrative control and warning signs, because this requires a human interaction. Human by nature tend to ignore direction given to them. That's the reason we don't follow speed limits on the road. Signs are there. Now, what are some of the methods? Let's look at that. We'll spend a little time. How do you eliminate during design? You put some low voltage controls. Finger safe terminal blocks. What do they do? A majority of the incidents start when somebody is working on it and they get a shock and they try to either continue or screwdriver hits somewhere else, causes a flash. One common thing you can do during design stage, and it cannot be done later, if you have different voltages in the system, for example, you may have 480 volt breaker in the same compartment as 120 volt control, you can isolate. So they are in different compartments. So when somebody is working on low voltage, they are not exposed to higher voltages. Now keep that in mind. All this does is gives you shock protection, unless the both cubicles are arc resistant. And one thing you can do, design for isolation of system. A good design starts from bottom up. You don't design a system and let maintenance people maintain it and operating people operate it. You see how they're going to operate and maintain, and that's how you design the system. Can the system be safely energized and de-energized? If you have, for example, double-ended two lineups, do you have two panels for control voltage so you can isolate? One thing also you can do, use smaller kVA transformers. Larger transformers contribute a lot of fault current, and that creates an arc flash hazard. Of course, to do that, you have to design the system. Transformer size is basically controlled by the largest motor. Instead of using a 3000 kVA transformer, you can use two 1500. Initial cost will be higher, no doubt about it. But if your life cycle cost, industry experience is that one arc flash fatality is close to $1.5 million. A arc flash third-degree burn injury is close to $6 million. So you can see how much money you can save. Okay? Next, look at the substitution. You can use arc-resistant equipment with door interlocking feature. That means it doesn't operate till the doors are interlocked. You can use high-resistance grounding system and give it the second fault priority. High-resistance grounding system, first fault would not cause any problem, but second fault happens, you may have full flash, so you can have second fault priority system. You decide which one is going to be taken off. Okay? You use insulated buses and use in combination with high-resistance grounding system, even though it may not consider as part of elimination, but at 90 to 95% it can be considered as elimination. Face-to-face fault will be protected by insulated bus, face-to-ground will be protected by high-resistance grounding system. Properly sized current limiting fuses and breakers so they can operate in current limiting range. Don't size the biggest fuse to protect the transformer. Take care of arc flash first. Okay? Then you have faster acting relays, for example, bus differential, zone selective interlocking, optical detection. Okay? Or you can have location of overcurrent device. When you have a transformer and you have a 10-foot bus duct or cable, the main breaker has the highest incident energy when the fault happens line side. You could probably put your CTs on the transformer bushing and trip the upstream device. Then look at some of the engineering controls. You can have maintenance switches, HRG system, interlocking. To assure, now maintenance switches, you do realize it doesn't comply totally under engineering control because it has to take some human interaction. Anytime a human interaction is taken, probability not following it is 1 in 10 in industry. Of course, all of you are shaking your head, I won't make a mistake, but people who are working for you might make it. So you interlock it, that you cannot close a tie breaker till one of the main breakers is done. High resistance grounding system. You can give a definite time that if you don't clear within a certain time, it will go in a trip mode. Now the least effective is the administrative controls, because now you're telling people what to do and you're expecting them to do that. Some of those are signs. You put signs, do not operate under these conditions. You put lights for alarm. You have safety programs. You have personal protective equipment. What is the common in all these things? You are expecting people to follow your directions. Lights and signs do not prevent somebody from doing anything. Safety programs teach people how to follow the procedures, but they are not there all the time. A safety program should always be followed by unannounced audits. Our people are doing that. Same way like police people do on the street. Signs are put in the speed limit, but then you're worried about you'll get a ticket. So audits are done. Personal protective equipment is the least desirable. Personal protective equipment as it exists now only protects you against two hazards: thermal flash hazard and shock hazard. It doesn't have any protection against blast. Blast pressure can literally blow you away. You do not have any protection against shrapnel coming in. Personal protective equipment can be penetrated. So the best method to do that from the top down is elimination or substitution. Elimination is harder because it requires a lot more effort. Substitution engineering controls are more cost effective. elimination you can do. High resistance grounding with insulated buses and second fault priority system. Have you eliminated? You have eliminated 90 to 95% time, and that's a pretty good odds. Okay. Now we'll leave some time for questions. I'll give it back to Mike. So, Mike, you can probably get the questions from the audience and pass on to me. Thank you so much for listening.
Okay, thank you, Dilip, for a very informative presentation. And thanks to everyone that's submitted questions today. Although there's no way we're going to be able to work through all of them in the next 10 minutes or so, we'll get started and try and answer the ones that we've prioritized towards the top of the list. I'd also like you to please take a moment to answer the feedback form that's going to appear on your screen. If you have pop-up blocker technology on, we ask that you disable it temporarily so you can receive the form. Okay, let me go ahead and get to the list of questions here, Dilip. And the first one says, what is the formula used to obtain the value of resistance on a high-resistance grounded system?
Okay. I assume the question is how you should sign your resistors. All you need to know what is your charging current of the system is. Charging current is defined as the capacitive coupling. If you ask a true engineer, they will tell you there's nothing like an ungrounded system. Everything is capacitively coupled. So you need your system charging current, and as long as resistor is sized above that, and you should be okay. Now, normally all these resistors are tap resistors, so you don't have to accurately calculate when you buy it. They may have 4 or 5 taps, and there are a lot of books available, references available. What is a typical system charging current? Unless you have a lot of underground cable buried in water, system charging current in 480 volt will be around 2 to 3 amps max. I hope that answers the question.
Okay, great. Here's another one for you. What will happen if a second ground fault occurs before the first is actually cleared?
That's a very good question. Resistance grounded system is based on that you will clear the second fault first before the second one happens, because it's limiting to ground. When the second fault happens, it goes face to face. So there are multiple methods to avoid that. One method always is do a good maintenance. As soon as the fault happens, you clear it out. But in my practical experience, most of the faults happen Friday after 5 o'clock when we don't have electricians available. So current technology which is available, that you can prioritize your feeders. So if you suppose you have 20 feeders on your switchgear, you can give a different priority to 1 to 20 to every one of them. And you are deciding which one is more important for you. So when a lower priority fault is existing, it'll alarm you. If a higher priority fault comes in, it'll trip the lower priority. That's an excellent technology. Anybody who's using high resistance grounding should very seriously try to utilize that.
Great advice. Thank you. Okay, the next question is, what do you do about a phase-to-phase fault?
Okay. This is essentially the same what I just explained. If phase-to-phase fault happens, high resistance grounding is essentially bypassed, or any grounding is bypassed. So what you can do, there are other options available. A pressure sensor, an optical detector. So or you can have insulated connections. An optical detector in combination with high resistance grounding will prevent the second fault from happening, because the first fault would not have that kind of arc to trigger the optical detector. When the next fault happens on the same breaker, optical detector will pick it up and isolate the fault. Okay.
All right, excellent. Okay, let's see. The next question, can I use a high-resistance grounded system everywhere, or is there a limitation on where I can apply this type of arrangement?
Okay. Essentially, there is no limitation. In National Electrical Code 250.36, It gives you guidance where you can use that. Only limitation is if you have line to neutral load, you cannot use that. So you need to probably put an isolation transformer. For example, if you have a 2000 kVA transformer that's high resistance grounded, and you need about 30 kVA load for lighting, which is maybe 12208, you'll have to probably put a transformer there. So only limitation is that where you have line to neutral load. We use that for very small system, even that we supply to UPS. 25, 30 kVA will use high resistance grounding. So look at Article 240.36. Now, if somebody's from Canada, I understand that they have some provision you can use where line to neutral is allowed as long as you trip it during fault conditions. So there's no limitation at all right now.
Okay, wonderful. This question ties back into your risk assessment matrix that you showed on one of those slides. And it says, does the matrix include the telecommunications industry working in a high voltage environment?
It depends. Anywhere there's a hazard of arc flash, it applies. Telecommunication industry use very big batteries. They use a lot of high voltage. So yes, it does apply. If people can get hurt, risk assessment should be done. If people cannot get hurt, then it's different. So, and basic premise of safety is every equipment has the capability to hurt you unless you prove otherwise. So yes, telecommunication industry is using risk assessment.
Great advice. Okay, the next question, will there be an arc flash, or could there be an arc flash, in a low-resistance grounded system?
Okay. Low resistance, anything above 10 amp, there will be an arc. But low-resistance systems normally are designed in industry to isolate on the first fault. So yes, there will be a fault. If you look at the medium voltage cable, which are protected by 1000 amp resistor, you see the cable has a hole in it. So yes, there will be definitely, unless it's a high resistance grounded system, there will be a fault, but it will be such a short duration that may not have much damage. Industry uses low resistance grounding system up to 138 kV, where the relays quickly take it off. Arc flash is also there in 5 amp. It just doesn't do any damage.
Okay. Next question. Can you discuss the fact that arc flash current is typically lower than a bolted fault current, and how does this impact the current limit capability of a current limiting fuse?
Again, that's an excellent question. In a 480 volt system, arc current is typical about 35 to 40% because arc has an impedance. And one example you can imagine, when you do welding, if you do not have any impedance, electrode will tie to the surface. So yes, arc fault is less. It's basically, if you look at 70E under NXD, it'll give you some idea. And fuse needs to be operated at arcing fault current. You cannot take fuse operating time at bolted fault current. So if you're using fuses as a rule of thumb, see if it'll operate at 33% of the bolted fault current. That is the time you should do. Again, that's a rule of thumb. Accurate calculation can be done by software.
All right. Excellent. Okay, here's everybody's very interested in data centers these days, and this question focuses on that area. What is the impact of a high-resistance ground to a computer room or a data center load?
Only impact is that'll make it safer. Data center main requirement normally is a common grounding system. All of our large data centers are all high-resistance grounding. It might mean that you may have to put a smaller transformer to derive your neutral there. Other than that, data centers are so critical that any interruption can cause a lot of damage, and you can see they would like to have a warning. So this high-resistance grounded, properly designed with proper equipment, is a custom made for data centers.
Great. Okay, is it practical to use arc flash within medium voltage 400 amp starters? And I assume they mean arc flash protection.
Okay. There will be a tremendous amount of arc flash in there. You can, if I assume you're talking about the questioner, if that's not correct, please send it to the I-Gard website. That optical detection can be used because if the fault is on the downstream of the fuse, NEMA E2 contactor, that will be a low duration because the fuse will clear out. But the fault will migrate, so consider using optical detection. And NEMA E2 contactors are the most widely known culprit in the industry for causing injury.
Okay, I think you answered this one, but it might be worth reviewing. With all visible light setups to trip centered around the optical arc detection technology, is there an issue with nuisance tripping?
That's always a concern. That's the reason I probably went through too quickly. You sense current along with it. So you are taking an AND gate. That means the current in that breaker has to be extraordinarily high and the light has to come the same time. That will reduce to a very acceptable level that false tripping. If you use optical detection by itself, if it's not a vacuum breaker, you can have a probability of false trip. So use that along with the current detection.
Okay. I think we'll ask one more question because this one sounds like it might be a little detailed, and then we're probably going to have to cut it off. So it says, you've explained a maintenance switch, a zone selective switch, and an optical arc detection device to reduce the time to clear the fault. What is the basis of choosing which one you would use according to what type of system you might be in?
Okay. There is one difference. Maintenance switch is a manually operated. Zone selective interlocking and optical detection are automatically operated. So anytime you have an option, and I'm not going to go through the cost, you can compare. An automatic system is always preferable to a manually activated system because human may forget to do what you want them to do, that they forgot to turn the switch when they're doing, or they forgot to turn it back, so which will cause an unnecessary trip. So anytime you have a choice, lean on automatic detection system. Of course, buy from a quality supplier. A poor quality equipment may cause you more trouble. So look at the automatic system. Optical detection is the fastest. Okay? Then the zone selective interlocking is next because that goes in instantaneous mode. And that's also automatic. The least desired is maintenance switch.
All right, I think that was a great way to kind of wrap things up here. I wanted to thank Dilip for a very informative presentation, and thanks to all of you that submitted questions today. I'd like to also thank I-Gard for being our supporting sponsor for the event today. And as for our audience members, hope to see you again at a future EC&M event. I'm going to try and hold these several times per year, so we'll look out for more promotion on these types of events. So everyone enjoy the remainder of your day, and we'll see you next time. Thanks, everyone.